Hi, we're going to look at lesson 1 of chapter 9. It is the continental drift hypothesis. And so let's start by just looking at our key concepts of the essential questions. So what evidence supports continental drift? So we're going to be looking at evidence that's supporting it. Why did scientists question the continental drift hypothesis? So they didn't accept it right away. When Wegener put it out there, they did not accept it. And so why? Well, because there wasn't evidence to support it, but we're going to be learning about that. Okay, look at the vocabulary. So we have Pangea, and that is the large mass of land where they call it a supercontinent. And so we're going to be talking about that. And hopefully you've already had a chance to, by the time you read this, have had a chance to put together the puzzle of Pangea, the online puzzle. Okay, and then we're going to be talking about continental drift as well. All right, this whole topic is continental drift. So how does this happen? Let's look at the bottom. In Iceland, elongated cracks called rift zones are easy to find. Why do rift zones occur here? Well, Iceland is above an area of the seafloor where Earth's crust is breaking apart. Earth's crust is constantly on the move. Scientists realized this long ago, but they could not prove how or why this happened. So, and that's the thing with this theory, the continental drift theory that Wegener came up with. A lot of people, I think, kind of agreed with him that his idea made sense, but he couldn't prove it. He couldn't tell how it was happening. And so we'll learn about the how in lesson 2, but in lesson 1, we're just going to learn about the theory. Okay, we are not doing the launch lab, so I'm just going to cross that out. Let's read about Pangea. So did you know that Earth's surface is on the move? Can you feel it? Each year, North America moves a few centimeters farther away from Europe and closer to Asia. That is several centimeters, or about the thickness of a textbook. Even though you don't necessarily feel this motion, Earth's surface moves slowly every day. So nearly 100 years ago, Alfred Wegener, a German scientist, began an important investigation that continues today. Wegener wanted to know whether Earth's continents were fixed in their positions. He proposed that all the continents were once part of a supercontinent called Pangea. All right, so this is his theory, that they were all part of a supercontinent called Pangea. Over time, Pangea began breaking apart, and the continents slowly moved to the present positions. Wegener proposed the hypothesis of continental drift, which suggested continents are in constant motion on the surface of Earth. Alfred Wegener observed the similarities of continental coastlines now separated by oceans. Look at the outlines of Africa. Here's Africa. I'm wrong. This is Africa. I guess that's from Too Little Sleep. There's Africa. And here is South America. All right, so let's see. He observed the similarities in their coastlines. And now look at the outlines of Africa and South America. Notice how they could fit together like pieces of a puzzle. Hundreds of years ago, map makers noticed this jigsaw puzzle pattern as they made the first maps of the continents. Evidence that continents move. If you had discovered continental drift, how would you have tested your hypothesis? The most obvious evidence for continental drift is that the continents appear to fit together like pieces of a puzzle. But scientists were skeptical, and Wegener needed additional evidence to help support his hypothesis. Climate clues. So Wegener used climate clues to support his continental drift hypothesis. He studied the sediments deposited by glaciers in South America and Africa, as well as in India and Australia. Beneath these sediments, Wegener discovered glacial grooves, or deep scratches in rocks made as the glaciers moved across land. Figure 2 shows where these glacial features are found on neighboring continents today. Because these regions are too warm for glaciers to develop today, Wegener proposed that they were once located near the South Pole. So when Wegener pieced Pangaea together, he proposed that South America, Africa, India, and Australia were located closer to Antarctica 280 million years ago. He suggested that the climate of the southern hemisphere was much cooler at that time. Glaciers covered large areas that are now parts of these continents. These glaciers would have been similar to the ice sheet that covers much of Antarctica today. All right, so there was an ice sheet all over it, and you can see that here. Okay, so if the southern hemisphere continents could be reassembled into Pangaea, the presence of an ice sheet would explain the glacial features on these continents today. All right, now we're on to page 309. Fossil cues. So the last thing, let's go back. The first thing we said for evidence was climate clues. Okay, so the first evidence that he could give was climate, other than the jigsaw puzzle, of course, climate clues. And then let's look at fossil clues as our second piece of evidence. So animals and plants that lived on different continents can be unique to that continent alone. Lions live in Africa, but not in South America. Kangaroos live on Australia, but not on any other continent. Because oceans separate continents, these animals cannot travel from one continent to another by natural means. However, fossils of similar organisms have been found on several continents separated by oceans. How did this happen? Wegener argued that these continents must have been connected at some time in the past. Fossils of a plant called, let me look at this, Glossopteris, I believe that's Glossopteris, have been discovered in rocks from South America, Africa, India, Australia, and Antarctica. These continents are far apart today, but the plant seeds could not have traveled across vast oceans that separate them. Figure 3 shows that when these continents were part of Pangaea 225 million years ago, Glossopteris lived in one region. Evidence suggests these plants grew in a swampy environment. Therefore, the climate of this region, including Antarctica, was different than it is today. Antarctica had a warm and wet climate. The climate had changed drastically from what it was 55 million years earlier when glaciers existed. All right, so it looks like here maybe they're starting to break up. So they went through an ice age. They went through a warmer stage where they had a fossil from this Glossopteris that was located in all of this space here. All right, so we've got two different bits of evidence. The climate clues. We've got where did it go? Fossil clues. Let's see what else we've got. We've got some rock clues. Okay. Figure 4 on page 310. If you could move North America and Europe next to each other, the Appalachian Mountains and the Caledonian Mountains would appear to form one continuous mountain range with similar formations. Well, we know from our from a chapter we did way back that the Appalachian Mountains are really old mountains. So this makes sense that maybe they are part of this rock clue that they're going to explain to us, because the Appalachian Mountains have had lots and lots of years, remember, to erode, and so they're more hilly rather than rocky, like the Rocky Mountains. All right, so we talked about that. Anyway, so let's go on. So rock clues, let's read about this. Wegener realized he needed more evidence to support the continental drift hypothesis. He observed the mountain ranges like the one shown in Figure 4 and rock formations on different continents had common origins. Today, geologists can determine when the rocks formed. For example, geologists suggest that large-scale volcanic eruptions occurred on the western coast of Africa and the eastern coast of South America at about the same time, hundreds of millions of years ago. The volcanic rocks from the eruptions are identical in both chemistry and age. Refer back to Figure 1. If you could superimpose similar rock types onto the maps, these rocks would be in the area where Africa and South America fit together. Okay, so back to figure 1. Back to my drawing where I accidentally got these confused. All right, so it looks like right where they fit together, somewhere in here, there would be these types of rocks that they're talking about. All right. Okay. Key concept check. How were similar rock types used to support the continental drift hypothesis? Well, they saw that there were similar rocks on parts of the continents that would fit together. And your book says, where am I? Page 310. Similar rock types in mountains, such as the Appalachian Mountains and the Caledonian Mountains, suggest that North America and Northern Europe were at one time connected as part of a single landmass. Likewise, similar volcanic rocks in Africa and South America suggest that these two continents were also joined. All right, so what was missing? Well, I think we've got plenty of evidence to support his theory, except he doesn't have a what? He doesn't have a how. How is this all happening? So Wegener continued to support the continental drift hypothesis until his death in 1930. Wegener's ideas were not widely accepted until nearly 4 decades later. Poor guy. Why were scientists skeptical of Wegener's hypothesis? Well, although Wegener had evidence to suggest that continents were on the move, he could not explain how they moved. One reason scientists questioned continental drift was because it is a slow process. It was not possible for Wegener to measure how fast the continents moved. The main objection to the continental drift hypothesis, however, was that Wegener could not explain what forces caused the continents to move. The mantle beneath the continents and the seafloor is made of solid rock. How could continents push their way through solid rock? Wegener needed more scientific evidence to prove his hypothesis. However, this evidence was hidden on the seafloor between the drifting continents. The evidence necessary to prove continental drift was not discovered until long after Wegener's death. Key concept check. Why did scientists argue against Wegener's continental drift hypothesis? Well, they argued because he could not explain how the continents moved. Okay, and we are not going to be putting this together. We're not going to be able to do that mini lab. But I hope you got to do the putting the puzzle together from the lesson yesterday. Let's go through the lesson review very quickly. Number 1, define Pangaea. Well, we can define Pangaea as a supercontinent that is made up of all the land masses on Earth. Number 2, the question says, explain how you can use models or demonstrations to explain the continental drift hypothesis. You could use puzzle pieces to model or demonstrate the continental drift hypothesis, which states that all continents once formed a single landmass and then drifted apart. Number 3, identify the scientist who first proposed that the continents move away from or toward each other. That was Alfred Wegener. He first proposed the continental drift theory. Number 4, which can be used as an indicator of past climate? Could you use fossils, lava flows, mountain ranges, or tides? You could use fossils because fossils will tell, from the fossils you can determine or infer what type of climate they would exist in. Number 5, look at the map of the continents below. What direction has South America moved relative to Africa? Well, South America has moved west. So South America has moved this direction. That's west. And Africa has moved east. Since Pangaea began to break apart 250 million years ago. Number 6, Copy and fill in the graphic organizer below to show the evidence that Alfred Wegener used to support his continental drift hypothesis. Well, let's move this down here. Let's make our own little one here. So the continental drift hypothesis. Don't make fun of my penmanship. Okay. All right. So what are some things that we just talked about? Think back. What are some things we just talked about that supported his theory? We saw that he could use rocks, like volcanic rocks that were in the same spots, or the mountain ranges that they talked about, that the Appalachian and some mountain ranges in Europe fit together well. He also used fossils. There was fossil evidence. There was some climate evidence, and some of that was with the fossils too, but climate evidence. And coastline. All right, so the coastline, the jigsaw puzzle looking thing of the coastline. All right, looking at our critical thinking, recognize the shape and age of the Appalachian Mountains are similar to the Caledonian Mountains in Northern Europe. What else could be similar? Well, I would say rock formations could be similar, and also maybe the fossils that they would discover there might be the same. Number 8, explain. If continents continue to drift, is it possible that a new supercontinent will form? Which continents might be next to each other 200 million years from now? Well, we just found out that that North America, I don't know where we read that, but that North America was moving towards Asia, right? So a supercontinent could be formed in North America. It says we'll move toward Eastern Asia, while South America will move towards Central America. India will be incorporated into Asia, and Northern Africa will collide with Western Europe. So, all right, we are done with this lesson for today.